My kitchen has a major problem. It's dark, dull, and that single overhead light isn't doing it any favors. It's time for an upgrade. Today, I'm going to show you how you can combine an ESP32, some LED lights, Home Assistant, and a custom PCB to transform the space from this to this. Let's get started. For this project, I wanted something that was clean, reliable, and high CRI, since you don't want the lights to alter the appearance of the food. I also don't want to use traditional RGB lighting strips. For starters, I don't like the white they produce, and secondly, I can't imagine a single scenario where I need a disco party in my kitchen. With all of those requirements, I've settled on these 24V 3000 Kelvin white LED lights from AliExpress, which even have a built-in diffuser. Since I'm going for a more professional installation, I wasn't going to settle for adhering the LED lights directly to the underside of my kitchen cabinets, as that wouldn't last long due to the hot steam and oils from food, and it wouldn't look very professional. With those requirements in mind, I've purchased some diffusers with some mounting brackets from AliExpress. Because I want to connect the LEDs to Home Assistant via Zigbee, I sourced this ESP32 C6. Zigbee is a 2.4 GHz wireless mesh network that was designed specifically for IoT devices. I like that Zigbee devices are not on the Wi-Fi network, which keeps them isolated from the internet. And since it's a mesh, the more mains powered devices you have, the better the network gets. The same cannot be said for Wi-Fi. You may have noticed that the ESP32 is 3.3V logic, and the LED lights are 24V. It is not possible to drive the LED lights directly from the ESP32's GPIO, unless you like magic smoke. I don't judge. You could use a relay to turn on and off the lights, but you would be limited to just on and off. Instead, you should use a MOSFET to switch the 24V supply to the LED lights. Simply underdriving the MOSFET's gate would reduce the brightness, but since the MOSFET is operating in the ohmic region, it basically turns into a resistor and will dissipate the energy as heat. Instead, you should use pulse width modulation, which will allow you to fully switch on and off the lights many times per second at various duty cycles, so that your eyes perceive a lower brightness. That way, the MOSFET will be operating in its saturation region, which is the most efficient. For testing purposes, I will be using the IRLZ44N logic level MOSFET to control the lights. To start, I like to test everything on a breadboard. This allows me to catch most mistakes before I order a PCB. My breadboard is currently wired as shown. Before you can upload your code, there are a few things that you need to make sure are set in the Arduino IDE before you can get started. First, make sure that the Xiao ESP32 C6 is selected in the boards manager. Under tools, make sure that USB CDC on boot is enabled. Without that, you may not be able to communicate with the ESP32 through the serial monitor. Don't ask how I know. Also, you want to make sure that your partition scheme is set to Zigbee ZCZR 4MB with SPI FFS. That will load all of the required Zigbee libraries into the ESP32. Now that all of those are set, we can go ahead and upload the code. In this example, I'm going to be using Zigbee to MQTT on Home Assistant. Now that the code is uploaded, all I have to do is click Permit Join on the Zigbee interface, and in just a few moments my device is connected and the interview is complete. As you can see, it's very responsive with no fires. Very nice. Now it's time to move on to the PCB. I wanted this PCB to be versatile, and I didn't want it to just be a one-off PCB for this project, so I included some extras that I might use in some other projects. This device has multiple MOSFETs for controlling multiple LED lights at once. It is intended that you populate only the required components for the channels that you wish to use, or if you do decide to control an RGB or even RGBW light strip, you can populate all 4 channels, which would be combined to control each color of the strip. While I was wrapping up the PCB design, PCBWay actually reached out to me and wanted to collaborate on this video, and the timing couldn't have been better. So I would like to give a huge thank you to PCBWay for providing the custom PCBs we're using today. PCBWay is a maker-friendly company that offers many services including CNC milling, 3D printing, PCB manufacturing, and even PCB assembly if your project requires it. PCBWay is dead simple to use. All you need to do is upload your Gerbers, and their tool intelligently extracts the detected parameters from your board. Here you can select various settings such as the quantity, thickness, and color. And with the PCB price starting at just $5 USD, you can get 5 boards delivered quickly and affordably. After nervously waiting 1 week in fear that I've made a mistake, the boards have arrived, and honestly, after quick inspection, the quality is great. Now we can get started with the assembly process. As I only have basic tools such as a soldering iron and a hot air station, I will be assembling these boards by hand. The first thing I'm going to do is assemble the buck converter circuit. That is because I have never used this buck converter before, and I'm the least confident about this part of the board. That way, if there is an issue at this point, I won't waste my time by fully assembling the board just to find out that it doesn't work. Now that pretty much everything but the ESP32 is assembled on the PCB, I'm going to test the power rails to ensure that I'm getting 24 volts and 5 volts respectively. That way I won't fry the ESP32. Now that the voltage rails are outputting as expected, I can install the ESP32 without any fear. And after one final test for shorts, I can plug in the ESP32. I have also designed a small enclosure in Fusion 360 that I will be 3D printing. The files will be included in the description down below. I'm going to be installing some brass threaded inserts. These will help keep the screws secure and should prevent the threads from wearing out each time you install and remove the lid. Now that all the parts are ready, we can install the PCB into the enclosure. With the controller ready to go, it's time to install the lighting into my kitchen. All I'm doing is measuring, marking holes with a pencil, tapping holes with the drill, and finishing them off with a screwdriver. I would also recommend ordering additional screws. The aluminium channels only come with the mounting hardware but don't include any screws. The only reason I had screws was because I ordered the joiners that included screws. Without that, I would have been screwed. I'm going to be installing the controller and power supply into the cupboard above my microwave. That is because there is a free outlet in there and that space is rarely used, so it's the perfect place to hide my project. For that, I will be using a microwave to drill a hole through the cabinet. For that, I will be drilling a hole through the side of the cabinet. That way I can discreetly run the cables down the side of my microwave. Here I am measuring and cutting a portion of the LED lights that I will need for that section. The lights include designated sections for safely cutting the strips. Now I can solder the wires onto the LED strip I just cut. And for the worst part, crimping JSTs. This part took me a few tries, but I got it in the end. Now that the entire strip is prepped, I can fish it through the hole I drilled and snap the channels into place. Since the channels are too long for my kitchen, I will be cutting them with a hacksaw. I'm sure there's a better way to do this, but this worked for me. Since the channels are metal, and metal is conductive, I will be wrapping the cable ends with electrical tape, which should hopefully prevent any short circuits. I will be adhering the LED lights to the channels so that it's easy to put the diffusers on. I also think that this will allow the aluminium diffusers to act as a heatsink to help keep the LED lights cool, which should prolong their life. Now for the other side of my kitchen. I have made this little joiner which will join the two segments of my LED light strip together. Now that the wires are prepped, I will pull the wire through the same hole I drilled prior. Because I don't think the connector will fit through the hole, I will be installing the connector after the wire is pulled through. And after applying some electrical tape, I can adhere the LEDs. So that I only have to drill one hole, I will be running the cable behind my microwave so that it can meet with the first cable I pulled through. Since the power supply I am using is temporary, it's actually from my Logitech steering wheel, the wiring is a bit of a mess for now. I will be ordering a more compact version for long-term use, and so that I can play Truck Simulator again. Now I can connect the LED lights to the controller. And after plugging in the power, there are no explosions. Very nice. I have also installed the Zigbee motion and light sensor, which will automatically turn on the lights once the kitchen gets dark and motion is detected. As a backup, I have included the Zigbee button on the wall as a manual override. And that's all I have for today. Thank you for watching until the end. I do have some other projects in the works, such as an automatic cat feeder, so make sure you are subscribed if you're interested.
Pardon me.